Okay, so here I have a thin convex lens. So when you get really thick lenses, you get aberrations that we don't want to get into. So we're going to talk about thin lens. And in fact, the physics assumption is that this lens is infinitely thin, which couldn't be true if it's going to be convex. But we sort of add the curvature that happens at both sides simultaneously to figure out what happens. All right. Now, we do know already that light that's coming in, remember if I have an object over here, this arrow represents my object, light is coming off in all directions, but light that's coming in parallel to the optical axis should go through a focal point. Let me put my focal point right here, about 3 units away on this set of axes, and it will bend like that. Whoops, let me turn my iPad to do a better job. There we go. That's a relatively straight line that shows what that light ray would do. We just put in primary ray number 1. Okay, so in terms of primary rays, remember right over here, we need to know what happens when it goes in and out. Light is going from all directions, but when it was coming in, it is going in parallel. It will go out through, I'm going to write the far focal point. We'll see why in a minute. Through far focal point. Okay, so that's ray number 1. All right. Ray number 2 is kind of the reverse of this. Okay, but what we need to realize is that a lens is reversible. If I had placed an object over here somewhere, light would pass back through the lens and end up converging on the other side. There's symmetry in this lens, so it will have a focal point that is the same distance. Okay, let me make sure I have 1, 2, 3, yes, 3 units on the other side based on where the lens is placed. Okay, so we have a focal point there. Okay, so we know, let me just change this to green. If light had been coming in this direction along primary ray 1, going backwards, it would come out through the lens parallel and back to where the original object is. Okay, so what we're going to do for primary ray 2 is this is the ray that goes through the focal point on the way in, but it's going through the focal point that would be on the near side. So I'll call that the near focal point. Light that passes through the focal point should come out parallel. Okay, so we can see how that would come out. So primary ray number 2 goes through, on the way in, it's through the near focal point. I'll just write FP to be shorthand, and it comes out parallel. All right, now we can see this will create an image if I were to put a set of eyes here and here, either 2 eyes on one head or multiple eyes, or we move around so that we can see where these rays are coming from. We would see that they actually meet right there. Let me get rid of that little blob here. So what we would see is, whoops, let me undo that. Get my pen back, make it black. We would see an image formed here, and the light rays really meet. So this would be a real image. It would also be inverted. Okay, and then it would, let's see, it looks like the magnification, it's hard to tell, but it looks like the size of the magnification might be about 1. So it's approximately 1 in this case. And there's a reason for that. The way I've drawn this, I have a focal length, F there, that is the same for both of these. So I have a focal length of F, and then I have an image length, a DI, right here, that's almost double F. So it turns out if DI is exactly double F, the image that you get will be in a 1-to-1 ratio. And I'll go over that in a minute. But there's a third ray that we need to consider. And let me put this in a deeper shade of red. Let me change up to a deeper shade of red here. There we go. And that's the one that would hit right in the middle. Okay. So if it hits the center of the lens, so it's in to the center of lens. Okay, the key is when it comes out, that's the flat part. It's like a flat window. So while there be a little bit of shift in side to side as it passes through, if we pretend that's an infinitely thin piece of glass where the faces are parallel, by that I mean right here and right here on the glass would be pretty much vertical. So it wouldn't bend the light. It bends on the way in, but then it bends exactly the same amount on the way out. So we continue in a straight line. So the center of lens, I'm just going to say it continues straight. Okay, now remember that's sort of our verification, right? That verifies that the image that we determine is in fact in the right place because the rays all coincide where we put the tip of that image. So the tip of the object would create an image where I showed. If you put a point right in the middle of the object, it would create we could trace those rays. It would just clutter up the picture and it would correspond to the middle of the image there. And if I took a point right down here at the bottom of the object, it would correspond right to the bottom of the image. And so we can see the whole image, but we're just tracing it for one point, which is at the extreme of the image, right? Now let's explain why this image happens to be about 1:1. It turns out there's a thin lens equation. And the equation that you generate is exactly the same as for the mirrors, because if I were to take everything on the right-hand side and reflect it back over the axis where the lens is, it would look exactly like the concave mirror ray tracing. Or conversely, if you took the concave mirror ray tracing and took all the reflected rays, flipped them over so that they were instead refracted, you would have the picture we have right here. So once again, we can say 1 over the object length plus 1 over the image length is 1 over the focal length. We're not going to get into how the focal length is derived, but you could do that. You could experimentally figure out the focal length by shining light from a distance and seeing where it converges. We can also say the lateral magnification is, again, the negative of di over do. Okay, so in this case, let's pretend that we have a focal length of, let's say 5 centimeters. Okay, and because this is a convex lens, that will be a positive 5 centimeters. It will cause the light to focus on the far side. Let us say that we have an object length of exactly double that, of 10 centimeters. All right, now we can do the math and we can see that 1 over 10 centimeters plus 1 over the image length needs to equal 1 over 5. It's not too hard to see that 1/10 plus 1/10 would be 1/5. So di must equal 10 centimeters. So you can do the manipulations, but you would see that di would be 10 centimeters. And then we can determine the magnification. It would be the negative of di over do. So it'd be the negative of 10 over 10, which is -1. All right. So what does a magnification of -1 mean? It means it will be inverted or upside down. That's what the negative tells us. And the 1 tells us that it would be the same size. Okay, so in the next video, I'm going to look at the ray tracing as we move the object around. All right, so we want to consider what happens when the object is far from the focal point, close to the focal point, and then inside of the focal point. So we'll look at those 3 cases in the next video.